It is exactly 2 o'clock, so I welcome you all for the first afternoon session. My name is Knut Reinhardt from Berlin, and I will be chairing this session. And we start with the first talk without much ado, and it's about using the power of big data and crowdsourcing for catalyzing breakthroughs in amyotrophic lateral sclerosis, and it's given by Robert Kueffner.
Thank you very much. So amyotrophic lateral sclerosis is a terrible disease. It's a neurodegenerative disease that affects the upper and lower motor neurons in the brain, and thereby destroys our capability to use our muscles. And so it leads to muscle weakness, paralysis, and eventually to death. And typically, after diagnosis, there are about 3 to 5 years till the death of the patient. But there are also a lot of exceptions. So Lou Gehrig, after who the disease have also been named, died after less than 2 years. And Stephen Hawkins lives now with his diagnosis for 40 years. And so this heterogeneity of the disease creates a lot of problems. So on the one hand, in terms of for the patients, in terms of clinical care, and in terms of clinical trials. So for instance, if you want to prove the effectiveness of a new drug, then you need large trials in order to overcome this heterogeneity, in order to prove the effectiveness. And in order to enable more scientific work on the disease, Prize for Life and the Neurological Clinical Research Institute created a database called PROACT that combines almost 20 completed clinical trials with more than 8,500 patients. And this database includes information on demographics such as age and gender, clinical information, if there's a family history of the disease, vital signs such as temperature, pulse, lab data, and functional measures. And it's open to the research community, so everybody that wants to can register and use it in their research. And so to improve patient care and improve the predictability of the disease, we started the ALS Prediction Prize in 2012. And thereby so this is an international crowdsourcing challenge where we solicited participants to use 3 months of the clinical trial data that we have in order to predict the progression over the remaining 9 months up to. So we look at a time period of a year. And as an incentive, we were able to raise $50,000 for the best predictive algorithm, so the algorithm that predicts ALS progression in the best way. And there are a lot of partners, Prize for Life, the DREAM projects, Innocentive, the National Cancer Research Institute, the Bowen family, and of course a lot of participants around the world. So that generated a huge interest. So we had more than 1,000 registrants from 64 countries, and most of the people that registered to get access to the data didn't have any prior experience with ALS. So these crowdsourcing campaigns, they can generate a huge interest for databases and also for developing new algorithms in order to tackle diseases that were difficult to cope with before. So ALSFRS, the ALS Functional Rating Scale, is one of the main measures used to judge on the progression of the disease. So it's a questionnaire, and it includes questions about the different muscle groups and the ability of the patients to use the different muscle groups. So can they swallow, can they climb stairs, can they cut with a knife, can they breathe? And so if you add up 10 questions, then you derive a scale from 0 to 40, 40 meaning the person is healthy regarding these muscle capabilities, and 0 means he has lost all his ability to use voluntary muscles. And as you see here, there's a huge difference in the disease courses. So there are very slow patients, very fast patients, nonlinear disease courses. And that is what I mentioned in the beginning that makes it so difficult to deal with this disease, both for the patients and from a scientific perspective. So this crowdsourcing challenge went like this. So we gave participants the first 3 months of data, and they had to predict the disease course over the next 9 months. And data does not just mean the ALSFRS that you see plotted here, but also all the other measures, all the demographics, lab tests, and so on that I mentioned on the last slide. The general approach participants took to prediction is presented on this slide. So there are some measures like age, gender, onset type that exist just once for every patient. And there's also longitudinal data where we have doctor's visits, and at these doctor's visits, the different measures were taken. And if we look at the second patient, you see we have essentially the same data, but of course the doctor's visits were at different points in time, and that makes the representation for learning algorithms a little bit more difficult. So meaning that where you have data once per patient, you just put them into a vector, and in order to create a vector out of the longitudinal data, you have to do some summary statistics, for instance, calculate a correlation, and then take slope-intercept correlation and so on, and put it into as a summary statistic into the vector in order to represent the longitudinal data for these lab tests or functional measures. And so we had 10 final submissions in this challenge. But I want to start with the baseline algorithm here. So if I go back to the last slide, if you have created such a vector, you can just use standard machine learning techniques in order to train models and do predictions. And so in this case, for the baseline algorithm, we use support vector regression. And there were a number of patients in terms of RMSD that scored better than our baseline algorithm. So for instance, this team 5 used random forest with essentially a similar setup, also using Pearson correlation as a summary statistics. And apparently with random forest, you were able to predict a little better. And the other algorithms that scored even better, they distinguished themselves by using different summary statistics. The best one actually used very, very simple ones, just the average, the first time point, the last time point, in order to represent this data. And there were also a number of algorithms that scored much worse than the baseline algorithm. We also did some bootstrapping in order to look at the statistics. And we determined that you have to go below 0.5 RMSD in order to be significantly better than the baseline algorithm. Nobody was able to do that actually. But by now, one of the winning teams funded a new company, and they do such predictions now with their company, and they were able to, after the challenge, improve below 0.5. And we also had a number of clinicians try to assess the same patients as the algorithms. As you see here with the axis, they scored quite worse than the two winning methods shown here in blue. So the two winning methods had a better correlation and a lower RMSD. And even then the best clinician that participated in this group. And these are world-leading clinicians in ALSFRS, so these algorithms on their own led to quite some improvement in terms of predictability of the disease. And furthermore, they identified several novel features. They identified features as predictive for the progression of the disease, like blood pressure, pulse, phosphorus, and creatinine. And so that offers new ways to look at ALS. So in addition, we did some trial simulation. So we simulated a trial with a linear model shown here. So we represented ALSFRS as some linear equation. So time multiplied by slope comes from the prediction, so that is the predicted slope. We also have a treatment effect and of course a remaining error. And then we can model the progression twice. Once by using the slope that was actually predicted by a given participant, and once by an average slope. And from the corresponding standard deviations, we can calculate the reduction in trial size. So assume that you would use t-test in order to determine whether or not a drug is effective. Then you would end up with a square of the ratio of these two standard deviations. So the standard deviations with and without the predicted slope. And what we found that way is that you could reduce clinical trials by a quarter in size and still see the same effects if you use these slope predictions. And of course, we hope for a little more, but even 1/4 translates into a $6 million reduction in the cost of a typical clinical trial here. So we are now I have switched topics slightly. We just launched the second version of this crowdsourcing initiative, the ALS Stratification Challenge. And if you're interested, look at this URL, which explains the way we think about this challenge and what we want to achieve. But I will very briefly introduce it to you. So what we did in the first challenge was to predict the disease progression. So what we wanted to achieve is that we wanted to distinguish those patients that progress rapidly into the disease from the slow progressors in order to give the patients and the clinicians a better idea of how to deal with these patients. And so now we switch gears a little bit in that, and we not only want to do predictions, but we also want to do stratification. So we're interested in finding patient groups that are characterized by different clinical features. So we're interested in patient groups where different sets of clinical features are predictive for their disease progression. And thereby we want to address the question is if ALS is just one disease, or is it maybe several diseases? So the large heterogeneity in disease progression points at that there might be several diseases involved, or at least several subtypes that have a strong influence on progression. And this is a challenge where we want to get at that. And here the slide shows a brief overview of the challenge. So as I mentioned before, we have a lot of ALS data for 8,500 patients, plus 4 new trials that are not yet available in the public domain that we will use as validation data. And the data that is currently in PROACT will be split into, will be used for training, and the new data will be split into leaderboard data and validation data. So the leaderboard data is for the participants that in the course of the challenge that they can check how well they are actually doing with their current algorithm, so they can do several submissions and see during the course of the challenge how well they fare in comparison to the other participants. And the separate validation data will be kept secret until the very end in order to do validation. So validation, of course, means that, for instance, you take the true slopes and the predicted slopes and assess the difference by means like the concordance index, Pearson correlation, or RMSD. And in order to make it happen, of course, to make the stratification happen, we needed to come up with a slightly more involved scheme for doing these crowdsourcing, this crowdsourcing campaign. So the way it's set up is like this. So you have to submit 2 executables, the selector and the predictor program. The first gets data for a given patient. So all the features that we have for this given patient will be put into the selector, and the selector is then responsible to do a subset selection, a feature subset selection, and only these selected features will be put forward to the predictor, who is then doing the final prediction. And the reason behind that is we have no gold standard for any ALS patient groups, so we cannot assess the grouping directly, so we have to do a slight detour in this. So we force the participants to just use a small subset of features for the prediction. They can choose the subset of features for each patient individually, so if they want, they can use different features for each patient. And by this restriction, groups of patients will emerge automatically. And in addition, we also ask for a cluster number. And by this, we think we will be able afterwards not only to assess the solutions, but also to assess the stratification. And in order to make that happen, we had to assemble quite a large challenge organizing team. So we have people that are associated with DREAM, such as Gustavo Stolowitzki, who will give the next talk, and Kelly Norrell, which is also involved. And we have a number of volunteers that were involved in previous challenges and that are doing a great job helping us to set this up. And then there's Prize for Life, again, which is also very important for this challenge because they were very important to assemble this PROEC database on the one hand side, and they're very involved in the organization of the challenge. The challenge itself will be done via Sage Bio-networks, and in order to submit executables and to be able that we can run these executables and thereby assess these methods, we involve the IBM cloud. So participants need at least do the predictions on the IBM cloud so that we can fully assess the submissions. When submissions are executable codes, I want to say that again. Thank you very much.
So, are there questions? Don't see any yet, but my question would be, do you think, this seems to be a very nice scheme to get people to work on challenges. Do you envision that could become more standard, that you have the next challenge and get some money to get people interested in it?
Yeah, so it's definitely becoming more standard. And so for instance, DREAM itself has created more and more challenges over the last 10 years. And so it's very, very interesting because it provides a separate estimation of this performance that is separate from the algorithm developers, and that has been shown a number of times that this is much more realistic than sometimes what is published and done by.
Another question.
Yeah, hi, Terry Gasterland.
Hi.
You may have said this in the very beginning and I missed it, but what is the source of the patients? Who are the people who are in this cohort?
So there's a PROEC database, and it combines 17 completed clinical trials. And within ALS field, the problem was that all these 17 trials failed. So no trial could statistically prove that the drugs that were examined had any effect. And so it was maybe a little easier to get them donated. But of course, that is the problem that we want to address to help make these trials more effective.
Yeah, and I ask in part, in Holland, the group in Utrecht receives all the ALS patients in the Netherlands. And I wonder if those are part of the clinical trial. If not, those are all very well phenotyped by one physician group who see many, many people over time. So that might be a source of a gold standard for you if they're not already part of it. I collaborate with them on a different disease.
I see. Thank you very much.
So any more questions? Time for one. If not, then we move on. Thank you very much.
Thank you.